For centuries, the moon's far side was a hidden mystery, a world of shadows forever turned away from us. But in 2019, that all changed. China's Chang'e 4 lander didn't just touch down, it uncovered secrets that are rewriting history. The lunar crust is not what we imagined. It's a patchwork of ancient impacts, and its environment holds a crucial truth about our future in space. The far side is no longer just a prize. It's an invitation. A new era of discovery has begun. In 2019, when China's Chang'e 4 lander touched down on the moon's far side, many analysts saw it as history. But the real story isn't only about technology. It's about what we began to learn afterward. New data on lunar geology, radiation, and even how the moon's crust formed in early history. These findings ripple outward, influencing models of planetary development. The story of one landing reveals a bigger shift, where fresh perspectives force experts to revisit ideas set for decades. And that's only the beginning of what we'll explore today: why the far side was the real prize. The moon's far side is more than just a hidden landscape. Scientists see it as a kind of untouched archive. Because it never faces Earth, it carries a record of early conditions in the solar system that has not been altered in the same way as the near side. In practical terms, the far side is the hemisphere of the moon that always points away during its orbit, locked by a process called tidal locking. That is why from Earth we never see it, and why for generations it carried an air of mystery. For decades, no space program had attempted to land there. This wasn't because of a lack of interest. The far side offers hints about how the moon's crust formed and about processes that shaped rocky planets in general. The main barrier was communication. Radio signals cannot pass through solid rock, and the moon itself blocks direct transmission to Earth. Any lander placed on the far side would go silent the moment it touched down. Without a solution, operations, commands, and data return would be impossible. China's program tested a way around this with an orbiting relay satellite named Queqiao. It was placed in what is called a halo orbit around the Earth-Moon Lagrange point, a stable position where gravitational forces balance. From there, the satellite could see both Earth and the far side at once. It acted as a middleman, picking up signals from the lander and passing them back home. This was the technical breakthrough that allowed the mission to go forward. Before this success, the consensus in the international space community was that a landing attempt on the far side carried unacceptable risk. The communications challenge seemed too uncertain, and the cost of failure was high. By proving the relay method in action, China didn't only succeed technically. It showed that operating on the far side could be reliable, setting a precedent other agencies could now build on. This is why the landing was more than just a symbolic milestone. It opened a door to a region that, until then, was out of reach. And once the lander and rover began working, their instruments started probing the geology of a terrain shaped by impacts and processes different from those on the near side. Warning signs that this site would overturn expectations began almost immediately. What made it scientifically valuable was not only the untouched nature of the landscape, but also the fact that the landing site sat inside the South Pole Aitken Basin. This is the single largest known impact structure in our solar system. Its floor and walls expose material from deeper layers of the moon's crust, layers that are not visible anywhere else. By being the first mission to touch its surface directly, Chang'e 4 provided access to information that theorists had only speculated about from orbit. After that point, the real focus shifted. The question was no longer about whether humanity could reach the far side safely. It became a matter of what secrets this terrain might reveal about the moon's deep past and about the larger history of planetary evolution itself. Unexpected clues in the lunar soil. When the instruments aboard Chang'e 4 started sending back data, scientists noticed something unusual. The rocks and layers beneath the landing site were not what most expected. The puzzle lay inside the soil samples and radar scans, which pointed to a composition that seemed out of step with common models of how the moon's far side should look. For a moment, it appeared as though a long-standing picture of lunar formation was missing some key pieces. The surface of the moon is covered by what researchers call regolith. In plain language, regolith is the layer of very fine, dusty soil mixed with small rock fragments that has built up over billions of years as the surface was pounded by meteorites and heated by the sun. It is often compared to powder, though it can also hide larger chunks of rock beneath. Chang'e 4's rover, Yutu-2, carried spectrometers and ground-penetrating radar to measure both the chemistry of this regolith and the structures hidden below. By tracking how radar waves reflected back from layers under the surface, the mission gave the first detailed cross-section of the far side's crust. Models built from earlier orbital observations suggested that widespread lava flows should have covered much of the far side with basaltic material. Basalt is a type of volcanic rock that is common in places on the near side we know as Lunar Maria, so expectations were that similar layers would dominate on the far side too, only with greater thickness. But the rover data did not fit this prediction. Instead of a surface rich in solidified lava, analysis showed minerals such as olivine and low-calcium pyroxene, which implied a different crustal makeup. The deeper radar scans revealed a set of repeating layers, not smooth sheets of cooled magma. These layers contained fragments of material believed to be ejecta, or debris, thrown out from past impacts. Some of these deposits extended more than 40 meters under the surface. In other words, the crust here looked like a patchwork of broken material stacked over time. Rather than being sculpted mainly by volcanic activity, the far side seemed to have been reshaped by a sequence of large impacts, burying older surfaces beneath younger debris. A useful way to picture this is to imagine rolling back a rug in your house, only to find that the floorboards beneath are made not of a single material, but of a strange mix of stone and rubble, unlike anything in the other rooms. The discovery suggests that the far side crust may have formed under conditions not shared with the near side. The broader implication is important. If each hemisphere built its crust differently, then the Moon is not nearly as symmetrical as once thought. That means models of its early mantle and its cooling history need to be revised. This uneven story of crustal evolution is now one of the key findings from the mission, forcing researchers to view the Moon's geology as more complex than a simple mirror image between near and far side. If the soil and rock surprised scientists, the environment itself would soon become the next source of questions, especially when considering the safety of future human crews. Radiation, survival, and the bigger picture. Beyond the rocks and soil, Chang'e 4 carried an experiment that had never been attempted on the far side of the Moon, a direct measurement of how dangerous the surface environment is for living beings. Most of the public discussion focused on the rover and geology, but for anyone thinking about long stays on the Moon, radiation is just as important. Without Earth's thick atmosphere and its protective magnetic field, the lunar surface is exposed to particles from deep space and bursts from the sun. Collecting actual numbers mattered because this determined how scientists could evaluate risks for future crews. Cosmic radiation means streams of high-energy particles that arrive from outside our solar system. They pass through space constantly and can damage DNA and electronics alike. In addition, the sun regularly throws out solar particles that strike planetary surfaces. On Earth, these hazards are filtered out almost completely. But on the Moon, nothing blocks them apart from soil or rock a crew might manage to hide under. Until Chang'e 4, radiation levels were estimated indirectly from orbital probes or measured inside spacecraft in low Earth orbit. That left a gap in knowledge about the actual conditions on the ground. To close this gap, the lander carried a German-led instrument called the Lunar Lander, Neutron, and Dosimetry experiment. It was designed to count the particles hitting the surface, identify their energy, and provide continuous readings over time rather than brief snapshots. This gave researchers their first profile of radiation directly on the far side terrain. The results confirmed that crews standing on the Moon would experience far greater exposure than astronauts on the International Space Station. The ISS benefits from partial shielding by Earth's magnetosphere, but the Moon offers no such protection. That outcome raised important questions about future missions. Continuous exposure at those levels means shields, underground habitats, or limited surface time would be necessary for safe operations. What was striking is that this far-side data arrived earlier than predicted. adding real numbers to studies that had relied on models until then. For China's program, these results provide a scientific foundation to argue for deeper participation in projects similar to NASA's Artemis plans. By supplying unique evidence, the Chang'e 4 mission positioned China not just as a follower, but as a contributor to the broader conversation on risk management. The mission also carried a biological experiment in a sealed container. Tiny plants and small animals, such as fruit fly eggs, were placed inside a controlled pod to see how they fared under lunar gravity and temperature variation. This was not focused on long-term growth, but on observing how life responds to the environment. While the experiment was short-lived due to temperature drops, it showed in principle how such systems could be tested on the surface rather than simulated on Earth. For space agencies and researchers, even such small-scale trials provide insight into the challenges faced by future life support modules. What emerges from these studies is a clear shift. China's contributions go beyond landing breakthroughs and into reframing what we assume about the lunar environment itself. Agencies now weigh radiation exposure data from the far side when drawing up crew safety models. By gaining measurements and biological results earlier than anticipated, the global community is adjusting its timelines and plans. With international partners preparing for the next round of missions, discussions now include evidence few expected to have so soon. Conclusion: China's landing on the far side of the moon did more than show technical skill. It shifted what scientists understand about lunar history, from the crust's structure to the real radiation environment awaiting future crews. Each dataset from Chang'e 4 now enters global discussions that shape where humans might safely explore next and how missions prepare. The consensus once assumed the moon's two sides formed alike, but evidence shows uneven development. Looking forward, the question becomes broader. What if the most important breakthroughs in understanding our solar system will come from regions once dismissed as unreachable or too difficult?